Learn how to present, right? You learn how to talk in front of people. We've already done a little bit of that. This is just another step in that learning process, right? So we're all at different points of learning, but yes, you're going to be graded today, but just think of it as a learning experience, right? So if you end up being a little bit nervous, that's okay, because it's more learning, more practice, and next time you'll do that much better, all right? So the other thing, we kind of learn how to work with people, right? So and it's been a very intense last few weeks, and you know, a lot of things get revealed during that time. So this is like the climax of chapter 7, right? And you know, and you'll have a little bit of time to reset and then go hard the rest of the way in the spring semester and finish strong. So so just relax today and have a good time. You're speaking about what most of you have been working on for a whole semester. A few of you have changed at the last minute and decided that your previous project wasn't sustainable, wasn't feasible, and so you're a little bit behind. We understand that, right? And this is part of the engineering process. Sometimes you work on a project and you say, you know what? We're not going to get there from here. And some of you reached that conclusion and had to kind of retreat a little bit to be able to move forward. So, so everyone just relax today, and but on a more serious note, I'd like everyone to repeat after me very carefully, okay? Rubber baby buggy bumpers. Rubber baby buggy bumpers. Rubber baby buggy bumpers. Okay, so, all right, so everyone relaxed a little bit, right? So we've all done silly things. So let's go ahead and have a good time today. So one last mention, no food or drink in here of any kind. So if you have that, no food or drink in the scholar room of any kind. It's your job, it's not mine, okay, if the dean takes you out. No, I'm just speaking for your own protection, right? So don't blame me. We have a couple of cool things this year. I think it's been done in the past, but we have restarted some effort to collaborate with other departments. And so the first two groups, you'll see that we're collaborating with the mechanical engineering department. In the first session, we're going to hear from a unified team. Well, hopefully you all are unified, but we're going to hear from the composite team. The next session is going to be kind of a solo presentation, but he's working with some other engineers also. The faculty and invited guests should have an assessment sheet here. So any other things? So I think we're about ready to get started. Now we're 5 minutes late, but we'll catch up somehow. So would like to now turn it over to the LC snipers. Go to View and Full Screen Mode, Control L.
How do you get it up on here? Like, it's only up there.
Oh, I'm sorry. Yeah, I can.
Oh, you can change the slides with the arrow stuff.
All right. Okay. Oops, I'm sorry. So now we'll. And sorry it's so hot in here, but it's not my fault. But next year we'll come in beachwear and we'll have some Jimmy Buffett music playing in the background. and we'll be more relaxed.
Next semester. Hello everyone, welcome to the Capstone presentations for fall 2016. We're here to present our project, the design and build of a device to automate the production of bottled chemical products. My name is Christopher Hoey and I'm a senior electrical engineer.
My name is Nicholas May. I'm a senior mechanical engineer.
My name is Robert Castellonia. I'm a senior mechanical engineer.
My name is Patrick Drennan. I'm a senior mechanical engineer.
And my name is Lauren Zavalian. I'm a senior electrical engineer.
Before we get started, we would really just like to acknowledge our two faculty advisors, Dr. Brent Horine and Dr. Zara Shabazi. For a brief overview of our presentation, as you can see here, however, I will be starting with the project motivation. We're working with a program called CREATE, which stands for Cultivating Resources for Employment with Assistive Technology, and this program is run by NICID, the New York State Industries for the Disabled. So CREATE essentially provides the seed money and inspires engineering teams, such as ourselves, to come up with assistive technologies designed with three main objectives. The first one is improving accessibility, the second one increasing efficiency, and the third one is developing professional workplace skills for the developmentally disabled workers at LifeSpire. Now, LifeSpire is actually a facility that is run by NICID. It works to produce the last 10% of any shipment order, and LifeSpire's mission clearly states that all individuals with disabilities can become contributing members to their families and their surrounding communities.
So the need for our project in today's market will be based off of satisfying our customer needs, which are the LifeSpire employees. The current chemical dispenser in use is not optimal for their productivity. First off, the buttons are in an inconvenient location, so we want to relocate them for ease of use. Second, the current dispenser does not have the capability of filling multiple bottles at once, so we want to automate that process to increase their productivity so that they're able to do other tasks such as labeling or packaging while filling the bottles. Also, the current hoses and spouts, while the chemicals are dispensing, there's a lot of sud formation which drastically slows down the process, so we're going to redesign those hoses to avoid suds from forming. Our main objectives are to increase their productivity because the employees do get paid per product they successfully package, and we want to make the system easier for them to use. A brief project description: we'll be designing an assistive apparatus that will be mounted on top of the existing chemical dispenser. We want to automate the process, keeping in mind our customers' needs, as well as the existing conditions in LifeSpire, as well as our budget requirements. And lastly, we want to make the system as hands-free as possible, implementing a single button press.
As Lauren mentioned, the main goal of our project is to increase the productivity of our workers. Therefore, we went to LifeSpire, the facility, and conducted an initial time study. For this time study, we asked the worker to fill up one box of chemicals. That's 4 one-gallon bottles. For this process, it took them 16 minutes and 33 seconds per bottle. That time is very high due to them waiting for the sudding of the bottles to naturally disperse. With this, it takes them, in their 50-minute hour, they can only fill up 3 bottles. We then asked them if they always do this process. They said they usually do, unless the order is rushed or they're behind schedule, and that way they will pour off the sudding formed by the chemical dispenser. This way they can fill up 4 one-gallon bottles, that's again 1 box, in 35 minutes and 48 seconds. This is much faster, but we're still aiming to increase this with our project. Our system will aim to automate a lot of the process and make a more ergonomic design for the workers. Also, with this automation, we want to make sure that we have safety features in place in order to protect the worker and prevent chemical spills. Finally, we want it to be clear and easy to operate because of who we're working for. This slide contains an overview of our design. In the background, you can see the original chemical dispenser. We'll start with the top. On the top is a linear actuator board containing 3 linear actuators. These linear actuators will serve to automate the process and are controlled by an Arduino microcontroller. The Arduino microcontroller is started by the color-coded buttons, which will be placed in front of our newly designed bases. These bases will be color-coded respectively to the buttons and have a couple of cool features involved with them. First of all, they have 2 nested rings. They start with a smaller ring that will support the 32-ounce bottle and the larger ring which will support the 1-gallon bottle. Also on the bases are 2 optical sensors. These will serve to detect the bottles and also for a safety feature. Just in case a worker knocks over a bottle, the optical sensor will realize that there's no bottle there and shut the dispenser off. Also, when you activate the button, depending on which bottle is placed on the base, the chemical dispenser will disperse that amount of chemicals. Also, within the bases themselves are load cells. These load cells will measure the weight of the bottles during the chemical filling process and will shut the dispenser off when the bottles are full. We've now attached different hoses to the chemical dispenser. As mentioned by Lauren, the chemical dispenser causes sudding, and that's because of the original hoses placed on the dispenser. Therefore, we're replacing those with long, flexible tubing. This tubing will go all the way to the bottom of the bottle, therefore significantly reducing the sudding caused by the chemical dispenser. Finally, we have an emergency stop button. In case any of our safety features go wrong or something happens, you can press that emergency stop button and it will shut the dispenser off with one push of a button.
Moving on to a little bit more of the electrical side of things, we'll start with the block diagram, where you can see that the 3 push buttons, as Nick has mentioned, each correlate to a respective activation of a linear actuator. This allows them to fill up 3 different bottles at one time, something that they're not currently able to do. And then you'll see coupled optical sensors working in tandem with a scale to work to deactivate the linear actuator once the scale has reached the appropriate weight for whatever the optical sensors have detected, whether it be a 32-ounce bottle or a 1-gallon bottle. And lastly, you'll see an emergency stop, which actually works to deactivate all 3 linear actuators at once in case of any emergencies. Next, we have a use case diagram which shows the interaction of the LifeSpire worker with the system in itself. So we have our first initial user interface where the LifeSpire worker will push either button 1, 2, or 3, and that goes over to our programmable hardware of the optical sensors and the load sensors, which will work to sense the bottle size and set the correct weight and measure the weight, working with the Arduino, which will either activate or deactivate the linear actuator based on the inputs. And then you have an emergency user interface where the LifeSpire worker will be able to press the emergency button, and that shows a more clear and direct path to the deactivation of the linear actuators in case they need to halt the process. Lastly, we have a class diagram where we have the Arduino inheriting from both an input class and an output class. The input class contains the buttons, the optical sensors, and the load sensors, as has been previously mentioned, and the output class shows whether it will activate or deactivate these linear actuators. And we have a filling station class, which shows that our entire system is comprised of these physical hardware components, and that the Arduino will be working to make our process work efficiently.
Here we have the key modules of our design. First, we have our microcontroller, which we chose as the Arduino Zero. We chose this because it has the capability to handle a lot of inputs and outputs. Specifically, it has 20 general purpose input and output pins. We'll be using 18 of those. Also, it's an open source technology, so a lot of information will be more readily available to us. And it's easy to upload the code to the board. In terms of where the Arduino will be located in our design, it's going to be mounted on the wall behind the dispenser to avoid any chemicals from spilling on it or harming it in any way. Next, we have the linear solenoid actuators, which we chose the TP8X16 actuators. A quick definition of what a linear solenoid does is it converts electrical energy into linear motion. So how that will work in our design is the linear actuators will be mounted on top of the existing buttons. So when the user presses the buttons that we have added to the design, a signal will be sent to the Arduino to activate those actuators to press the existing button. We calculated the amount of force needed to press those buttons to be around 2 pounds. So the rated values that we chose that are included in this solenoid are more than enough to accomplish that. We also measured the depth of the button depression to be 0.5 inches, and this particular solenoid has a stroke length of 0.75 inches to ensure that the button will be completely pressed. Lastly, in order to operate the solenoid, we'll need to devise a solenoid driver circuit. On the right here, you can see we have created a test circuit that we did on a different solenoid. Once we get the funding and are able to purchase the solenoid we need for our design, we'll be able to recreate this circuit on our particular solenoid.
Next, for the module that we'll be talking about are the optical sensors. So we needed something that detected either the presence or the absence of a 32-ounce or gallon bottle, and therefore we needed a photoelectric sensor in reflective mode. And that's precisely what the TCRT1000 optical sensors do. They work best at a distance of about 1 millimeter, as you can see from the characteristic diagram on your right-hand side. Considering in our design, the optical sensors are placed flush against the top of the bases where the bottles will be placed. This works out pretty well considering the distance between the optical sensor and the bottle shouldn't exceed 1 millimeter. And it was very easy to choose these optical sensors considering they were in stock and inexpensive. And also when we implement these, The circuit that we will be using involves a pull-up resistor and an amplifier so that the signal to the Arduino is clear enough for it to read to act as a safety feature.
Major problem with the original chemical dispenser are the original hoses that were placed on the dispenser. You can see that these are rigid hoses and don't extend very far. This causes two problems for the worker. One, they usually have to hold the bottle all the way up, and also it causes chemical sudding, which is a big problem for us. Due to this, we're going to be removing these hoses and replacing them with flexible tubing. Again, these tubes will extend all the way to the bottom of the bottles and significantly reduce the sudding. Next, inside each base, as mentioned, are load cells. We're going with the TAL220 load cells. These load cells need to be very accurate, and therefore these load cells have an accuracy rating of 0.00 pounds, which is perfect for our application. Also, they have a maximum weight of 10 pounds. Again, that's perfect for us. 1 gallon bottle with our chemicals weigh a maximum of 8.5 pounds. With the load cells, the output signal of them is too low for the Arduino to read. Therefore, we have to bump up that signal with an HX711 amplifier. This amplifier is easy to use, has a lot of step directions for us, and also has an output voltage of 3.3 volts, which is perfect for the Arduino. These scales, here's an example of it right here. You can see they're strain gauges, so they'll place the bottle right here, and they'll tell us the weight of the bottle. Also, they're accurate, they're compact, and they're inexpensive, perfect for our design.
So talking a little bit more about our hardware setup that we have here. So as you can see, we have 3 different buttons. They're all color coordinated, and this is to help ensure that the LifeSpire workers can actually differentiate between each of these buttons. And as Nick mentioned earlier in the presentation, these buttons are going to be connected with the nested rings that are going to house both the 32-ounce and the gallon jugs that will be filled with the chemical solution. Each of these buttons will also correspond to a shape and a number for those individuals that may be colorblind. And each of these buttons here are 2 inches in diameter, so they'll be easy to see. And then off to the side here, you can see that we have a much larger emergency stop button. This is to basically give the LifeSpire worker the ability to halt any operations that may be going awry while the dispenser is in use. For our risk analysis, there were a few things that we had to keep in mind as we were designing this. Our chemical hazards, so chemicals that may have characteristics that we need to design around, such as corrosiveness. Filling the wrong bottle size, again, as Nick mentioned earlier, we have nested rings, which will help to identify whether or not that bottle is going to be filled for that specific location. And then for accidental button pressing, where those buttons are going to be located, so that way they're not in an easy to reach spot where they might be pressing them by accident. And then finally, the hose obviously not being placed in the bottle. With our new flexible design, now the worker needs to actually actively put the hose inside of the container. A little bit more on the chemical information. As you can see here, we have 3 different chemicals that we're going to be using for this dispenser. Breakdown XC, Morning Mist, and Virex2. Now something that we found was that all 3 of the chemicals were found to have the same density, and this actually worked out great for us because the load cells that we have that are going to be sitting in the bases, they don't need to be calibrated for any one specific chemical, obviously because all of them have equivalent densities. And as you can see here, they're all very close to the density of water. Now, one other thing that we found was that 2 of the chemicals, Virex2 and Morning Mist, were both shown to be corrosive chemicals. And with that, we're going to be using that information to help design around our bases that we will be creating to protect both of our mechanical hardware as well as our electrical hardware.
So many of our components are off-the-shelf components. However, some of them we will need to manufacture ourselves, and for the ones that we will need to manufacture ourselves, we need mechanical drawings for. Here you can see our linear actuator board. At the top right here, we'll mount 3 linear actuators to be over the existing buttons on the chemical dispenser. This is a mechanical drawing for our scale bases. If you can see here, there are 2 pass-throughs for our optical sensors, as well as our nested rings for our 32-ounce and gallon bottles, and a space underneath for us to mount our load cells, which will measure the weight of the bottles as they're being filled and turn off the dispensing. Here are the dimensions for our optical sensors, which we mounted in our pass-throughs to our scale bases. These optical sensors will be potted in, flush mounted with the top of the scale base in order to make a watertight and accurate level for the optical sensors. Here are the mechanical drawings for our load cells. Our load cells will be mounted underneath our scale bases and use a Wheatstone bridge to determine the strain on this cantilever type load cell. So our test plan includes in constructing a prototype. We will get our components in and construct individual circuits, make sure that everything works. We will then, in doing this, test our programming logic and ensure three major things: that we have good bottle detection, that we have linear actuator motion, and that we have accurate wave measurement. We will then take all of these individual circuits and put them into a prototype, and then fit this prototype to a chemical dispenser in order to make sure that everything is working the way that we want it to. Here are our bill of materials. On the left here, you can see many of our raw materials. Some of the things such as wood sealant, cable sheathing, and the paints. The paints will be used to color code the different components in order for the LifeSpire worker to differentiate between the chemicals, as well as our wood sealant and our cable sheathing to protect our electronics components and our manufactured components, our manufactured wood components from being infiltrated by chemicals and protect them from the corrosiveness. On the top right here, we have our electronics components, including our Arduino, our buttons, our linear actuators, and our optical sensors. And on the bottom right here, we have our original estimate, which wound up being about a little bit over $1,000. However, since our original estimate, we have changed a couple of our components. For example, we changed our Raspberry Pi to now it's an Arduino, as well as we reduced the cost significantly of our linear actuators, and have gotten our total cost down to $640. Here's a schedule. Currently we are on our December 5th. For the mechanicals, it was our critical design review. For electrical, it's preliminary design review. But we will be moving into next semester with ordering parts. We will ensure that each one of these parts works once we receive them in, as well as we will test the programming logic when we assemble individual circuits using these components. We will then take these circuits, put them into one large prototype, and then take this prototype and fit it to the dispenser at LifeSpire and get feedback from LifeSpire, making sure that the dispenser is doing everything that the customer would like it to do.
Okay, so in summary, what we are doing here is we're designing an apparatus that's fixing a productivity issue presented by LifeSpire. We want to raise the productivity so the workers will be able to get paid up to an hourly wage. We don't want to replace the workers with our automated process. We want to assist them. So, and also our funding is coming from NICID's CREATE program. We would also like to acknowledge NICID for giving us the opportunity to do this project and provide us with funding, as well as LifeSpire for giving us access to the facility, and they've been very gracious in that process. And lastly, we would like to thank Manhattan College's Electrical and Mechanical Engineering Department for giving us guidance and technical support. Questions?
So we got time for a quick question, perhaps?
Yes.
Is there some sort of fail-safe, other options, like just in case your worker doesn't know that something's going on that's wrong, like as a backup?
Yeah,
Like safety
in our design we have the optical sensors which detect the presence of the bottle, so if they do press a button without a bottle there, the Arduino will not start dispensing. Also, if a bottle happens to get knocked over while it's being dispensed, the optical sensor will also sense that, and it will not dispense as well. And then we have our load cells, which if there is more weight than the desired amount, it'll stop. And so those are different fail-safe mechanisms to prevent anything from happening.
Really nice job. Okay, I thought it was very smoothly done and everything, and it really made me feel like this is going to work when you build it. I just had one question, because I didn't understand about the actuator that we're using. I was concerned about when you said that the hose is going to go deep down inside of the bottle. How does the person get it out? Does it automatically come back up at the end so
No,
that
it's
they
a
can remove it?
flexible tubing, so they're able to, oh, you mean like how the actuators
How do they get
into
the bottle out afterwards is what I'm asking.
So
It's
there's
now
enough-
full. Is the hose still in the bottle or has it been automatically removed?
So currently there's enough space in between the dispenser of the bottle itself and the countertop where they'll be easily able to just lift the hose out by themselves. And we're thinking about putting a cap on it right now that will stop any chemicals that are still on the hose. So when they pull the hose out, all the chemicals that are still on it will go back into the bottle instead of spilling anywhere else.
All right, well, that's, I think all the time we have. Thank you very much.